Hi everybody, in the last tutorial video we looked at how to define the node class in Python and how to construct some nodes and how to give them the correct data and also how to push those nodes into a node array. Now I'm not going to review that video in this video because it's going to swallow all my time and this is going to be quite a long video. So if you're not sure about the last video, you'll have to go back and watch it again or do some research or do something about that. Okay, this video we're going to move on. We're going to be looking at Task2.4, write program code to add a new data item to the binary tree. Well, here is the binary tree. Let's imagine that we want to add the color turquoise to this tree. Okay, so we've got a new node with some data, turquoise. Probably doesn't have any pointer information at the yet. It doesn't know anything. It's just a new node. We're going to try and put it into the tree. So the new node, turquoise is greater than maroon, so we go right. Turquoise is greater than silver, so we go right. Turquoise is less than violet, so we go left. Turquoise is going to go here. As you can see, turquoise's pointers are none. This is a leaf node. What we have to do is update violet's left pointer. Now that we know where to insert the node, we simply need to update the parent node's pointer. Okay? Now, let's say that we create a search pointer, and we're going to search through the tree until we reach a leaf node, because that's where we can insert a new node, at a leaf node. So we're looking for a leaf node. We're looking for a none as a pointer value. Okay? So let's say we set the search index to be 0. We start at the root node and we start the logic. So turquoise is greater than maroon, so we go right. So our search pointer becomes the index of this node. Let's say it's 2. Turquoise is greater than silver, so we go right again. So search pointer now has the index of this node. Let's say it's 8. Turquoise is less than violet, so we go left. We go left. Search pointer now has a value of none. That's a problem, because now we don't know where we are in the tree. We don't know that we recently visited index 8, or whatever this index is, because search pointer has updated to none, which is fine because that we need it to do that. That tells us that we've reached the end of a path and we're now ready to insert a new node into the tree. But we don't want to lose the reference to the latest node that we visited. We need to store that information as well. So hopefully you understand what I'm talking about, and I'll try to cover that as we get coding. Okay, so the first thing we want to do is let's just create a new node. I'm just going to say new node is equal to a node object. Remember, at the moment it doesn't have any pointers. It's a new node. It's going to be a leaf node. So that's our new node at the moment. Now I'm going to put this node into the array. I'm not putting it yet as part of the binary tree. I'm just putting it into the next available element in the array. Okay? So how do we do that? I need to find the first instance of none in the array. This would be, for example, the free pointer index that maybe you've come across in your studies in computer science. So the free pointer is here. This is where we're going to put this node. So I'm just going to write a little bit of code to do that. Let's say pointer equals 0. Let's start at the beginning of the array. While nodes pointer doesn't equal none, we're simply going to update the pointer. Now this will work in this example because we do have some nones. But if we didn't have any nones, the pointer would go out of the array. We'd get an out of bounds error. So I'm just going to clean this up a little bit. Just make sure that pointer is always less than the length of the array. Okay. So by the time we get out of this while loop here, one of two things has happened. Either we found a good index, or pointer has become greater than the length of nodes. Okay, that means there's no space in the array. So if pointer is less than len nodes, well, that means there's space. So let's put this new node into this array. So that's the first bit done. We've put the new node into the array, but now we need to put the new node into the binary tree. Okay? So we discovered that this new node is going to sit here. Turquoise is going to be here. Let's just go back to my original idea. Violet has an index of 6. Violet has an index of 6, and remember, turquoise has an index of 9. So Violet's left pointer is going to become 9. At the moment, Violet's left pointer is none. So that's going to change to 9. Okay? And this Violet is at index 6. So there's a few things that we need to figure out here. So let's update. All we have to do is update a pointer, actually. We're going to update the parent's left or right pointer. Okay? So the first thing we need to do is search for the place to insert the new node into the binary tree. We need to search for that node. Okay, so I'm going to create a search pointer, and I'm going to assign it a value of 0. Now, while nodes search pointer no, that's not true. Sorry. While search pointer itself doesn't equal none. Remember, when search pointer equals none, that means we've reached the end of a path in the tree. So while search pointer doesn't equal none, we're going to traverse the tree. Now, do you remember, we need to make sure that we always reference the latest node that we have visited. Because when search pointer becomes none, if we won't know where we are in the tree. Okay? So I'm just going to make another pointer and just assign it to search pointer. Okay? So we always save the latest value of search pointer before we update it, because eventually it will become none. Okay? Now, if nodes search pointer dot get data is greater than our new node's data, then, well, let's just think about that. If the node in the tree has data which is greater than the new node, if the node in the tree has data which is greater than the new node's data, we're going to go left. We're going to follow, the search pointer will follow the left pointer. It's going to go left. So search pointer will be updated to the current pointer that will work, well, the node where we currently are, dot get left. Else search pointer is going to be updated to node's search pointer dot get right. And using that logic, we're just going to work our way through the tree until search pointer becomes none. That's when we've reached the end of a path, and we now have a place to insert our new node. So let's do that, and when all of that's finished, let's print current pointer, because that will tell us where we are in the tree. When the while loop's finished, let's go and print current pointer. Yes! It's 6! Why am I celebrating? Do you know why I'm celebrating? Do you remember? We determined that turquoise will go as a left child of this node. This node, according to my design, is at index 6. So we found the correct node to do the insert. Brilliant! Now then, can we finish this? What we need to determine now is whether we're going to update the left pointer or the right pointer of this node, which is violet. We've arrived at the violet node. Okay? So if node's current pointer dot get data is greater than new node dot get data, we're going to update the left pointer of this node. So I made a method called set left, and we're going to update the left pointer value with the index where we placed the new node, which was 9. Do you remember? And I used a variable called pointer to do that. So in my program, this currently has a value of 9 because that's where I put the turquoise node. Else, node's current pointer, which is the node that we're currently at. Is that right? Pointer. Okay. So what I'm going to do is, if I can, I erased it? Oh no, I erased it. Let's just create a for loop here for x in nodes x dot to string, and let's run this thing and see if we get an answer. Pew. Yes, violet has been updated. Its left pointer is now 9, which is the index of the turquoise node. Now, we're getting this, of course, because we still have some nuns in the array. If x doesn't equal none, then let's do that. Let's just run it again so we get a clean output. Yes, it works. Now take some time to consider this video and communicate with someone if you're still not sure what's going on, because this is one of the key topics in paper 4.